Hello everyone, today I'm going to talk about challenges faced in mitigating side channel vulnerabilities inside LLVM. Let me start with some background. Safety critical code needs to be hardened. When I started working on security, it was very surprising for me that security people don't care about securing things which is not a secret. So security people only care about secret, and the software that deals with secret, let's call them safety critical code. Here are a few examples of some safety critical code, like password hash comparisons, cryptographic key quality checks. We do not care about general purpose code, we only care about hardening these safety critical cryptographic code. A little bit on side channel as well. So side channel works by leaking data through unintended side effects. So for example, suppose your program wrote something into cache and someone was seeing your cache, or someone was indirectly reading your cache to extract that data. There are other type of side channels like timing side channels. Suppose you have a program in which when you provide a password, and if the password matches, it runs faster when the password is wrong. Now, these things may seem trivial, but these informations can be used by a malicious actor to extract the password, to leak other stuff. But to deal with these things, constant time programming has always existed. As the name suggests, constant time programming means that you write a program in such a way that its execution for every input does not generate any variable side effects. So for example, you will write your code such that you do not have any branches on your secret data. Or for example, if you have a big list of things, you will iterate over whole list. You will not exit early of that iteration because you found what you want to find. But is constant time programming enough? Unfortunately, no. So we have seen with Spectre meltdown that there are possible attacks which can also break your constant time programs, but that's not it. Even if you have a program that is perfectly constant time, now there exist so many different microarchitectural side channels which comes from your caches, your prefetchers, that can still produce noticeable difference that the attacker can use to exfiltrate data. So what are these microarchitectural side channels? Suppose you have a constant time code. It looks like that this code should execute in constant time, but then the hardware can decide to do some optimizations internally. These microarchitectural optimization can make the execution of your program to have different side effect than it would have when those optimization would not have been present. So one of the most popular one is speculative execution. Then there are others, silent store, computation simplification, and I'll give examples for these. Speculative execution is simple, that what we see here, we see a condition and then we see a move. Now, actually in the program, the condition was if the index is under the bound, then you do this move. But the CPU decides to speculatively execute the move and then roll it back when it realizes that this condition doesn't hold true. But during that speculative or that transient execution state, your cache is already changed, your cache state has already affected, which can help the malicious actor extract things, and we have seen how serious Spectre was. But this is a complex example. Let me go to a very simple example, and this is my favorite. It's called silent store. Suppose you have two stores to the exact same address, but they have different registers. What happens in the hardware, that if these two values are same, if the value of EAX and EBX are same, then the second store is just silenced, it's just optimized, right? Like in the hardware, we have these store buffers, we can see what are the stores that are coming, in what order they are coming, so it makes perfect sense. Why do we want to go to the store cycle again and waste those precious cycles? But then this information can also be used by people. Have shown that this simple attack, like this simple optimization, which seems very trivial to us, like even as compiler engineers, right? Like this should happen and we would expect this to happen, but from security standpoint, this is bad. This is really very bad. Similarly, a much simpler example, suppose you have an ad. What do you expect when one of the registers or argument is 0? I expect that it should not go to the ALU or whatever the complex circuitry is for it today. It should directly return the second argument because a plus 0 is a. This can this can generate a timing difference. So now when one of your variable is 0, the attacker is know that this variable is 0 because add returned faster compared to this other thing. So these microarchitectural optimizations, which are very necessary, like we cannot get rid of them, they may create side effect which can be observed by an attacker and can do data exfiltration. The biggest takeaway is that these things break your constant time code. So all the effort that has been gone into writing all this constant time cryptographic libraries, and constant time programmer hate compiler people because we undo their effort. Like they write this program which is constant time, and now we have these optimization inside the hardware which is kind of doing the same thing. One thing that we realized is that there are code patterns in our program which we as a compiler engineer, we focus a lot because we see those code pattern and we transform them into a more efficient and a more optimized version. But what we also realize is that these code patterns are also used by the hardware to trigger these optimization, which may be potentially vulnerable. So can we not just turn off the optimizations which are bad? We cannot turn off speculative execution. That's like that will be a big performance drop. Can we not turn off these for people who care about security? Like, can you give me a button on my laptop that is off? Probably not, because no one has so far released such a thing. Can we turn it off programmatically that now my crypto code is getting executed? Turn this off. Now it's like, now I don't care. Like I'm in a non-critical section of my program, run it normally. This is somewhat possible, but still the support for this is very less. The example that I gave you about the add instruction, you'll be surprised in Intel instruction set, the add was variable timed. So I think last year or last to last year, they released a flag. When you use that flag at OS level, not programmatically from your program, when you use that flag at OS level, they make sure that your add is constant time. I was very surprised to know that that simple operations like add, multiply, and other arithmetic operations were not constant time. So what do we do? Like we have seen this other side that it triggers this microarchitectural optimization. What else can we do? So this side of this thing is, can we get rid of all the code patterns which should not trigger those optimizations? So for example, if we know that this particular piece of this particular region of my program deals with secret, can I transform that part of my program such that when the thing gets executed on a hardware, it never actually trigger those optimizations? And this is smart, but this is also complex because we have to cover all the possible cases. But it turned out that this is a great fallback and a backstop solution because you can do it at day 0. You can do it for older hardware. So this is a day 0 solution. A new attack comes out, you can push out this mitigation inside your compiler. Everything now compiled with a compiler does not call the optimization which was potentially vulnerable, and this thing also works with your old hardware, right? Like you don't like, even if the vendor fixes the bug, the vulnerability, or even provide some support, it will be provided in the future hardware. And we have seen with this with some we have seen with this Apple M1 chips. Like there was an attack. It's called Augury. It's based on the data dependent prefetcher. It came out. The M1 was vulnerable. The M2 was vulnerable. But in M3, M4, it's either fixed or there's a way to turn it off. We need to perform a taint analysis on the program that we have to figure out that what are the regions in our program on which deals with secret, and these are the regions which we care about should not trigger these optimization, and then we transform them. The simplest case, the Spectre, which most of you will be familiar about, that we put fences, right, to stop that speculative execution. And it's the same concept, but it's just that we already use this in practice. So suppose this is the code which was vulnerable, and let's say that somehow this code is in the critical section or some section which is safety critical, we put a fence. And because of this fence, we know that this move will not be done speculatively, and this is actually in a way turning off the optimization to happen. And if we can do at right places at right time for right data which we know are secret, we can efficiently protect our secrets from getting leaked from Spectre without having to go through that performance drop of turning off the speculative analysis, speculative execution completely, or even doing it for all the things in the program, like putting fence before every move. Similarly, for silent store, you had two moves. What if I put one more move in between them? I put one more store, such that I guarantee that R11, the value in R11 is never EAX and EBX. So what we actually do is we take the value from EAX and EBX, we split them. So we take the upper half from EAX, we take the lower half from EBX, and we invert them. Now, doing this, we guarantee that the value that will be generated will never be same to EAX nor EBX, making that now silent store does not trigger for EBX because R11 is R11 is never same as EBX, and it also never triggers for R11 itself because R11 is not equal to EAX ever. So I hope that I was able to give some intuition about how these attack works and how we think is the way to disable them, mitigate them inside the compiler by these selective code transformations. Now let me address some challenges that we as a we faced while we were implementing these. Like I have been implementing these for past 2-3 years now for attacks of different complexity. The first challenge is that where should we implement these things on? Like we have this amazing transformation, we know that how to turn it off. Where do we implement it? Should it be LLVM IR pass? Should it be a backend pass but before register allocator, or should it be after register allocator? Suppose that you care about all the stores like silent store, and we want to transform, or we want to care about all the stores. Probably we want to do it after register allocation when the spills and the fills have happens, and we know that these are the new stores when all the passing variables through stack has happened and we have all the store that can possibly be emitted. But then there are mitigations where that level of abstraction is just too low level. For example, you want to allocate shadow memory, you want to somehow deal with shadow memory, you probably want to do it at LLVM not at MIR. At that too, after register allocation, it just becomes a lot painful. So this is the first challenge, and what we have realized is that there is no good solution. What worked best for us was that whatever works best for LLVM let's do it at LLVM. Let's go down. Let's keep tagging things. Like let's keep that information around that where this thing comes from. Another interesting thing is that if we want to implement silent store transformations after register allocation, we need to reserve R11. And this is a very common practice. Like if you see some of the mitigation passes also written in bold, temporary registers are needed. But for us, inside LLVM code, we have to reserve R11 for x86. We have to do it manually. Like there is no better way of doing that. But these are the things that these changes even the way the compilation cycle behaves. Okay. The next challenge is, where do I schedule my pass? I have written this mitigation pass. It works well. Where do I schedule it? Ideally, I want to schedule it at the end because I don't want anyone to undo it. I don't want any other mitigation to undo it. I don't want any other optimization to undo it. But if everyone is at the end, what is the end? Right? If you have one mitigation pass, sure, put it at the end. If you have two, what about the phase ordering between these two? And if you have 10, and given that how this how the new threats are emerging, how new attacks are being found, and also how memory safety is in a very good direction of finally being tackled, and probably memory safety will not be as big of a challenge in, let's say, in the next decade, and side channel will become a bigger challenge because we will probably solve memory safety. there is also this perspective shift that when we do optimization, we figure out the only thing that we care about, it should be equivalent and it should be fast, right? And we figure out, these are the low hanging fruits, these are the places where we are 100% sure it will be equivalent and it will be fast. But for mitigation, you cannot miss anything. If you miss a store, if you miss a code pattern, that's false sense of safety. That's a potential vulnerability, and that's a much harder vulnerability to find because you claim that this is a mitigated binary. So some open research questions are that me as a person who is writing this pass, how can I reason about passes that are ahead of me? And this also goes with the pain of people who are writing constant time programs, that they want to use compiler, they want to have their constant time program to be fast, but the problem is the compiler is such a complex infrastructure that it does things in a way that is not trivial to realize until it's done. So this can also help people who want a compiler for constant time program to work. And there's one other thing, like how can we figure out conflicting transformation? How do we know that this undo this, and this thing is complementary, this subsumes this? Similarly, one of the biggest challenges that we faced was inline assembly. Inline assembly inside a compiler is just a string. What do we do about it? Like if you have a mitigated binary and you didn't handle you didn't handle inline assembly, that's no good, because there are still a lot of places where our attacker can find gaps and go in. For our experiment, what we did was that almost all the crypto libraries, they have a version which does not have inline assembly, like a non-highly optimized version, and we use that. But the best way to do it is to do it in bold or a binary, like a binary rewriter. But then it also has its own challenges, because you cannot bring all the analysis result in, even a taint analysis just to tell you what are secrets is much better if you do it at LLVM IR level. And things like dealing with shadow memory. Suppose you have to create a shadow memory and use it. It might be a challenge to do it at bold. But also there is this another perspective, right? Like to figure out that are these two transformation conflicting, or to figure out that how do I order them? Did I do right? Did I do wrong? Sure, like that will require having semantics for each transformation, having to figure out, and inst combine pass, right? Like there are things that are huge to even think about such semantics to be even written down. But then can we not have simple post transformation checkers, like this is the binary I generated, does this have this code pattern? And these are simpler things which can be implemented with a binary rewriter, and that we actually do that. So once I implement, I do not do it on, I do not use bold for this, but once I implement mitigations, I take the binary, I write a checker, and then I check it, like are there anything, is there anything that is left? And surprisingly, a lot of the time when I thought that I did a great job, I realized that there are so many code patterns and things that I missed. And compilers are so complex, the backend is so complex. So to even support all the stores, sure, you can write a MIR pass after register allocation, but to support every stores at the place where it was made. So for example, I want to double the size of all the stores that are generated in the backend. It's painful, because you have sizes for calling convention, you have a lot of various things going on. To conclude, I would like to have you I would like you to have this takeaway at the end of this talk, which is this, that compiler-based defenses are really flexible and timely responses to these emerging threats. You have new attacks coming out tomorrow. You can push out a compiler-based mitigation much faster, and we have seen this during Spectre as well, that compiler-based defenses came out really quickly. I 100% agree with the sentiment that these things are slower, but I also believe these things are necessary, because you cannot go back and change the hardware. Like I use a laptop with M1. If I care about the attacks that are on M1, I probably have to move to some other. I probably have to move to some other, a newer hardware that has fixed that, or maybe these compiler-based transformations, because I only have to apply it on the cryptographic code, the code that actually deals with our passwords, our private keys. And if you think from a bigger perspective, how much is this code versus the total code that we use? Probably small. How much is the overhead? Probably huge. But if you look from the bigger perspective, this huge overhead on the smaller part of code is manageable. And compilers are amazing infrastructures, and well suited for optimization, transformations, analysis. They were actually never made for mitigations. So that's why we are facing this challenge. We're not saying that compilers are bad, like they are bad for mitigation. They were never made for mitigation. But there is a place to improve compilation infrastructure in a way that mitigation can also be a part of it. With that, I'd like to thank you all for coming here.
Hi, thanks for the talk. That was really thought-provoking. I had a question, which is, how did you evaluate whether your program transformations were effective? And in particular, I'm interested in, what if, for example, like the silent store optimization, like what if a compiler, what if, on one piece of hardware, that's enough to trick the the microarchitectural optimization, but like on a newer piece of hardware, perhaps already also in existence, that doesn't work. Like, how do you validate these sorts of things? And also, as new pieces of hardware come out, how do you check that some mitigations aren't regressing other mitigations? Like, what's sort of the evaluation strategy here?
Correct. So the thing that we implement is very architecture as well as microarchitecture specific. So suppose we implemented something for x86, this particular microarchitecture is just work for that. We do not claim that it works for anything like any other version that the new version that comes out. The interesting thing is that a lot of our stuff is also very dependent on attacker community who figure out that this particular microarchitecture is vulnerable to these things, and they do a decent job in giving out the information of the attack that this is how the attack is. I can say that these transformation at this point are so simple that if you see if you see just the spec that this new attack came out, it works like this, and you ask like, will this transformation work for it, you'll probably get answer by yourself. But right now we do not do that.
Thank you.
Any other questions? No. Okay. Yeah.
Thank you,
So
everyone.
we have lunch now, and the sessions will re-begin at 1:15. Thank you.